we're talking about radiation that can remove electrons from atoms. What kind of radiation is considered ionizing? As you can see, we've got X-rays and gamma rays. Do you remember what we said was the difference between X-rays and gamma rays? Right, how they're produced, right? X-rays are produced outside the nucleus, right? So what are the two ways we produce X-rays? Characteristic, right? Both of those happen outside the nucleus. So gamma rays, we said, were emitted from the nucleus itself. Okay, that's our distinction. Okay, other people will say X-rays are lower energy, gamma rays are higher energy. That's not as clear cut, so don't worry too much about that. We have alpha particles. What are alpha particles?
How is it there?
2 protons and 2 neutrons. Right? Alpha particles are these big, chunky particles made of 4 subatomic particles. What's a beta particle?
Another form of like.
It's an electron.
Yeah.
That's right. Beta particles are just high energy electrons that are flying around.
And what is alpha?
Alpha is a really giant, chunky particle made of 2 protons and 2 neutrons. Right, so alpha particles approximately 8,000 times larger than a beta particle. Okay?
You said 2 protons and 2 neutrons.
2 protons, 2 neutrons, correct?
Alpha is bigger.
Alpha is bigger, much bigger. It's the biggest particle we have up here.
So beta has more mass. No.
Beta is 8,000 times less.
Less.
Mhm.
So
Yes, Tricky.
the gamma rays are produced outside the nucleus.
No, in
Like,
the
in
nucleus.
nucleus. And X-rays are produced outside the nucleus.
Correct. Okay. Yes, Jay.
Sorry, one more time. So you said the beta particle is 8,000 times smaller than the alpha particle, or
Correct.
just the? Okay.
And then as far as protons and neutrons go, right, we can get these ejected during things like photodisintegration or proton therapy. So, lots of different types of radiation. Depending on the kind of radiation, they have different effects. Right? So, we can talk about what effect or what is the difference between, yeah, they're having lots of fun over here. All right, let's also have as much fun here.
Speaking of
Too
fun,
much
Yes.
fun.
Miss Laura told me that she had to Wilson-proof everything that they taught back then,
Yes, that's true. I remember her telling me that as well.
and that you were also asleep most of the time.
Mm.
So
Yeah.
I,
I don't want
I just wanted to come to the source because she's speaking on your name.
We'll talk about that after class.
Okay.
Still absorb the material.
What did she say?
No.
Let's go.
Because he was me apparently. You know how
So-
I asked the questions. Yeah.
What?
So
So
it
what
was
are
in
the
light.
what are the properties of those types of radiation we talked about that affects how they interact with the body, with molecules? The main things are charge, mass, and energy. When we talk about charge, what does charge sound like?
Iron.
Ions, right? Electrical charge, right? So does it have a positive or negative charge, or is it neutral? Right? So, X-rays. Do X-rays have a charge?
No.
The neutral. So
No, they are neutral. Good. Does something like an alpha particle have a charge?
Yes.
alpha is positive. So
Yes.
Yes, positive charge,
Yes.
right? Because it has 2 protons, gives it a positive charge. Why does that make a difference? Because if you have an alpha particle that's positively charged and it passes by another atom, because it's positively charged, are electrons attracted, repelled, or not affected?
attracted. So
They're attracted, right? Because electrons are negative, the alpha particle is positive, it attracts electrons. So do you think it has an easier time or a harder time removing electrons from other atoms? An easier time, right? So the charge of the alpha particle means that it has a much easier time to ionize other atoms and molecules because it's able to pull electrons off a lot easier. Hey, mass. So, mass, right? How much stuff there is in an object. If something is more massive and it crashes into something, is it going to have a bigger effect or a smaller effect?
bigger
Bigger.
effects.
bigger effect, right? The more the mass, the bigger the effect. So once again, if you have something with a lot of mass, like an alpha particle, it's going to have a bigger effect when it interacts with another atom.
Yep.
Yes.
So velocity doesn't matter in that sense?
And that's where we come to energy. Great segue, thank you.
You're welcome.
So, when we talk about energy, right, kinetic energy, when we're dealing with things that have mass and kinetic energy, what sort of factors play into that kinetic energy? Does anyone remember? All the way back from physics, I think.
Mass, the energy time, sir.
So,
The force, right?
okay, so it does deal with force.
Joules per kilogram, weight and
Right, so we're
energy.
going to be dealing with acceleration and velocity, right? And we're also going to be dealing with mass, right? Energy is based on mass and acceleration and velocity. So, the faster the particle is traveling, the bigger the particle is, the more energy it's going to have, right? More energy is going to have more effect. Now, for radiation like X-rays, right? Electromagnetic radiation, photons, energy, photons, this does not have mass. They only matter as mass. Energy does not have mass. So when we talk about energy in terms of electromagnetic radiation, does anyone remember what we do instead?
So what? What was the question?
So when we said, okay, when dealing with matter, like an alpha particle, we look at mass and velocity and acceleration to determine its energy. Something like a photon, like an X-ray photon, does not have mass. It is not matter. When dealing with something like a photon, what determines its energy?
Frequency.
Frequency and wavelength determines the energy of a photon. Okay. So, the higher the frequency, the more energy the X-ray will have. Okay. So, to kind of talk about how these differences in our types of radiation can affect the body, we have three concepts that we need to go over. We have LET, RBE, and OER. LET being linear energy transfer, RBE is relative biologic effectiveness, and OER is oxygen enhancement ratio. Now, at least one of these three terms should sound familiar because we did cover it with Ms. Bonilla last semester.
Let's.
Yes, LET, linear energy transfer.
The amount of energy deposit in tissue, no?
Amount of energy deposited in tissue
Don't, that's all I know. Don't.
over over its path. Right?
Over what?
Over its path.
Okay.
Over where it's travels, right? Because when we talk about linear, the word linear has the word line, right? We're sort of
Okay.
talking about a line, right? So this radiation travels in a line. Okay, so in this case we call this track, right? This is the path that energy takes through the body. So this is the track, this is the line that it's traveling along. And as this radiation travels along this track, it is giving off energy into its surroundings, right? It's crashing into things and it's losing energy as it travels through the body. So the question becomes, how much energy is it giving off as it travels through the body? Is it giving off a lot of energy, or is it only giving off a little bit of energy? Right? If it gives off a lot of energy, then the radiation itself is going to lose that energy. On the other hand, if it doesn't give off energy, it keeps most of its energy as it travels through the body. So, this is important because if you have a kind of radiation that travels through the body and does not give off any energy, will that radiation have an effect on the body?
No.
No. That kind of radiation would be just pure transmission. It would not do anything to the body. On the other hand, you have a type of radiation where as soon as it interacts with the body, it gives off odds energy. Will this have any effect?
Yes, sir.
Yes. Right? Because if it gives off odds energy, that energy is going to do something to the
So what
body.
energy you said?
The energy of the radiation.
No, what energy it will give off?
the energy, so radiation comes in, it has energy. If it interacts with the body, and that radiation gives off all its energy, that energy is going to interact with the body.
Gives off all energy, is the word you're using.
As an example, yes.
Give off.
Now, so we need to talk about, right, how much energy is being given off. Does it give off nothing? Does it give off all of it? Or is it somewhere in between, right? That is linear energy transfer. We say, in this distance, as it travels through this distance, how much energy did it give off?
Okay.
That is all linear energy transfer is about, right? Don't overcomplicate it. We just look at a certain distance and we say, how much energy was given off as it traveled from here to here, right? So we take an X-ray and we're like, how much energy did the X-ray give off when it traveled from here to here? Then we take a beta particle. How much energy did it give off going from here to here? You take an alpha particle. You ask, how much energy did it give off going from here to here, right? That's linear energy transfer. It's that simple, just. How much energy did it give off when it traveled from point A to point B? Okay. So, right? Energy deposited over the length of that travel. So linear energy transfer is just energy deposited divided by the distance it traveled. Okay? How much energy did it give off over this distance it traveled? That is linear energy transfer. So the higher the LET, the more energy is given off within that distance. So if we're to talk about how dangerous radiation is, would we say dangerous radiation is high LET or low LET?
High energy, sir.
High LET, because if it gives off a lot of energy in the body, that is going to be dangerous, right? So, X-rays have an average LET of about 3 kiloelectron volts per micrometer. This is low. X-rays are considered to be low LET radiation. Other types of radiation are going to be higher LET, so they give off more energy as they travel through the body. Why is this important? Because when that energy is given off, that energy can go to ionize atoms and molecules. That energy can go to break chemical bonds. And as we discussed last chapter, DNA is just a bunch of chemical bonds, right? You've got your nucleotides, you've got your adenine and your guanines, and they're bonded together. And then, right, you've got them in a chain, and those chains are bonded together, right? And so if you have energy coming in, that energy can break the bonds in the DNA and cause damage. Low LET doesn't cause as much damage, breaks fewer bonds. High LET, lots of energy, so it can break many more bonds, cause a lot more damage. Okay? So our low LET radiations are X-rays, gamma rays, and electrons. When we say electrons, what kind of radiation is this?
Photoelectric.
Beta.
Beta particles.
Oh.
Remember, beta particles are electrons. So X-rays, gamma rays, and beta particles. These are low LET radiation.
I thought it was hot.
They're low because they do not give off a lot of energy in the body. They can travel through the body and pass through and keep a lot of their energy.
But alpha has high.
Correct. Alpha is the high one.
Do we need to know or memorize the average for the each? Or because in the last time you had the one for X-rays.
This one, not too interested in the exact value.
Okay.
Sir?
Just know low versus high.
Okay.
Yes,
The
Shaheen.
electrons are radiation by, the electrons are radiation or beta particles?
Beta particles are electrons as radiation, yes.
Thanks.
So, when we look at low LET radiation, this radiation is highly penetrating. It's highly penetrating because it keeps most of its energy as it travels through, right? If it loses its energy, it's not going anywhere, right? It got fully absorbed. So these are highly penetrating. They go through, they keep their energy. These have a poor ability to ionize. Because they're not giving off a lot of energy, they can't do a lot of ionization. These interact.
Can you repeat that again? The poor ability to.
So because they're not giving off a lot of energy, they're not interacting a lot, there's not a lot of ionization happening. These interact randomly along the track, right? So whether or not they bump into something is just up to chance, right? These are not things that will interact with every single thing that they pass by. And so these do not lose energy very quickly, right? That's what we also said. These don't give off a lot of energy, they don't lose their energy quickly, and that's why they can pass through matter. Okay. So it makes sense, right? X-rays. X-rays can pass through the whole human body and keep their energy. Right? Gamma rays, electrons, same thing. Yes, Shakti.
So only if they interact, because something comes on the way that then they react, and they, if they don't, if it's just going in between, then it goes through.
Yep. Generally speaking. At least for low LET radiation. So, low LET radiation primarily interacts with the cell through something we call indirect action. Now, we first talked about direct and indirect action all the way back in summer 1. Does anyone kind of remember what the difference was between direct versus indirect?
Indirect is through the, go ahead.
Okay, yes, Matsu.
Well, indirect, what, like,
Okay.
it means the radiation
It's like
is,
radio-
interacting with the
when it
water
hits the water,
in the
yeah.
cytoplasm,
There it is.
outside the nucleus.
Yes.
Good.
Direct is within
That's
the
correct.
nucleus, the DNA.
That's right. So, radiolysis, right? So, indirect versus direct. Well, first of all, earlier, what is the molecule we were talking about? The important molecule to the cell?
Water.
DNA.
DNA and water.
Water is also important,
Yeah,
that's true.
see, yeah.
But the main one, the master molecule, is our DNA.
All right.
That is the master molecule, yes. So,
Yes, Master.
Yes,
let me
ma'am.
talk about, no, you can refer to me as DNA. So,
Yes, Master.
let me talk about the DNA.
No, February.
If something
Hey.
interacts with the DNA,
You know
right,
that.
if something hits the DNA and interacts with it, that's direct, right? It's directly interacting with the DNA.
You said it hits what? Say it again. Direct is what?
So if radiation directly interacts with the DNA, that is direct action.
All right.
On the other hand, if the radiation interacts with something else, and then that something else then interacts with the DNA, that's indirect, right? So it's like, if I owe you money, right?
Mm.
I could give you the money directly, so that's direct action, or I could give it to my friend to give it to you. That's
'Cause you know I'm about to-
indirect.
No,
I know I'm about to come at them femurs.
Now, of course, I would need to trust my friend to give you all the money.
You trust him.
Right?
Trust that friend.
Don't trust the friend,
Don't
all right.
trust Melanie, no.
So, indirect action, right? Here, our low LET radiation is primarily interacting with stuff other than the DNA, right? Why? Because because low LET radiation, because it doesn't give off a lot of energy, it doesn't do a lot of damage to the DNA. And we said last chapter that DNA can repair itself using enzymes. Enzymes can repair DNA. So if an X-ray comes in and they're like, look, and they kind of damage the DNA a little bit, enzyme comes along, fixes it, and everything's good. So it's not going to cause a lot of damage that way. The damage from low LET radiation comes when the X-rays interact with things like the water, right? Radiolysis. And now the water has what we call free radicals, and those free radicals then attack the DNA, right? So indirectly damaging the DNA. That's where the damage from low LET radiation primarily comes from. Right? So the production of free radicals. Rather than attacking directly, the radiation created this intermediate that then attacks the DNA.
So in indirect,
Mhm.
that's when radiation hits something and then it hits DNA
Right. so-
second or something like that?
correct. So it interacts with something else first,
Okay, uh-huh.
and that something else then interacts with the DNA.
All right.
And that free radical is always created with water, sir.
So we primarily talk about free radicals with water, yes. Because 85% of the cell is water,
Water.
right?
That's why it interacts with the cell.
That's right. Okay. So in contrast to low LET radiation, this is high LET radiation.
Yeah.
Primarily our alpha particles and our neutrons. Right? These are our big, chunky particles with lots of energy. Okay? So, something we find about high LET radiation is that they are poorly penetrating. Because they give off most of their energy really, really fast, they don't get to travel very far. They have a strong ability to ionize. Right? We said, for example, alpha particles, they have charge, they have a lot of mass, they have a lot of energy. So they have a very, very good ability to ionize. They can rip electrons off of other atoms and molecules. Okay? And then these rapidly deposit their energy. They enter the tissue, they quickly give off other energy, and then they stop. Right? So rapidly deposits energy, poorly penetrating. These are the key factors for high LET radiation.
So they don't.
Okay, Reagan first.
Which people?
Reagan and then
Please,
Shahid.
Okay, explain one more time the penetration part of it because you would think that if it had higher energy, it
So-
would be better.
Mhm.
I don't know.
Okay, so the way to think about this, okay, let's say that, all right, imagine outside, we've got that hallway, right? With the two doors on the end, right? That really long hallway, right? We're along the hallway, right? The security desk is there, and there's two doors at the end. Okay, now, someone in a motorcycle crashes through the door, comes down the hallway, and then crashes out the other door. Right? How much damage did they cause?
Oh, a lot of them.
So, what did they damage?
I mean, only
The
the
doors.
doors on both.
Doors, door, right? Anything else?
And also
No,
things
sir.
in the way,
They took
inside
out-
the
Anybody-
cell.
Maybe
The
security
room.
as well.
The,
Maybe some poor
Ah.
patient.
the
Maybe
patient that
maybe
can't get out
they
the
might hit up
way.
between the student.
Not
Okay.
very much though.
So, now
I know
let's
you did
compare
not.
this to an 18-wheeler that comes crashing through that front door.
Out of there.
Now, okay,
That will do
how much damage is it going to cause?
A lot.
A lot more.
Yeah.
But
But it's
this thing you're
stop
going to
halfway.
go all the way through the
Yeah,
hallway.
It's gonna
Yeah.
stop
It's gonna
halfway.
stop.
It's a fast
It's
one.
going to stop, right? So, high energy, but it gives off most of its energy to cause damage, and because it gave off all its energy, then it stops in the middle of the hallway.
It's gonna stop,
Right?
yeah.
But it's
Motorcycle.
high LET.
So-
Low damage, so it keeps most of its energy, travels through.
So that would be high.
So, the truck is high LET, the motorcycle is low LET.
I'm sorry, repeat that again.
So, the truck, the 18-wheeler, would be considered high LET,
Okay.
and the motorcycle would be considered low LET.
So whatever stays inside is the low.
So, if it stays inside, it's high LET.
So the motorcycle was high.
Motorcycle travels through. It came through one door, it exited the
Oh,
other
okay,
door.
okay. So that's high?
So if it travels through, it is low LET.
So that's like an X-ray.
Okay? Because it does not do a lot of damage.
Low.
Low LET, less damage.
X-ray.
Okay.
Big truck crashes through the door, breaks all of the walls and everything, but then stops halfway through. So that's high LET.
Low. I got it with less damage.
Not this guy.
Less damage.
That's a great way to think about it. Less damage, low, right? 2 L's, right? Less damage, low.
Yeah. Less damage.
Okay. Shahina, the question, and then we'll go to Jay.
Sir?
Yes.
Sir, my question is answered. I will just want to confirm it, sir. That means alpha particle will not complete the part if it stop inside the cell only.
Yes, alpha particles stop early. Yes, Jay.
I was just thinking of a different example.
Different example?
I think it's been confirmed, so thank you.
So, pop quiz. If you wanted to stop an alpha particle, how much stuff do you need to stop an alpha particle? A sheet of paper. Why can you stop alpha particles with something so thin?
But they're less energy.
That's right.
Open gives
They
that.
hit the paper, they give off all their paper in the, or all the energy inside the paper, and they don't go through. Alpha particles are high LET, so they're poorly penetrating. They quickly give off all their energy. You can stop them with a sheet of paper. Low LET, X-rays. Is this gonna stop an X-ray?
No.
No, X-rays will travel through, right? X-rays are high penetrating, but they don't lose energy quickly.
Makes sense.
Okay, yes, Jay.
So to keep the sheet of paper analysis or
Mhm.
whatever, if you had a bowling ball, that would be the alpha particle, and if you had a needle, just pushing both, like the needle is going to be able to go through, but if you were to push a bowling ball, it's really not going to.
Needle
Yeah,
will also
that
break the
works.
board.
That works. So, because high LET radiation has a poor ability to penetrate matter, like our alpha particle, this actually isn't very dangerous if it comes from an outside source, right? So if this telephone right here was just giving off alpha particles this entire time, it's actually not that dangerous. Just protect myself, and that's it.
Maybe your shirt will protect yourself.
Yeah, the shirt's gonna protect me even, yeah. However, if these alpha particles enter the body, so let's say I eat the telephone now, and now it's inside my body and it's giving off alpha particles. That's when it becomes dangerous. Right? So if you implant it, right, if it gets stuck inside the body, or if you eat it, like swallow it, right, or if it's injected, or if you breathe it in, that's when alpha particles become very dangerous.
But if the phone comes out, then that means it's low.
Okay.
So is it like
You said you
chemo?
eat the phone, so if it comes out, that means it's less energy, so that's low.
Okay, not like that. Not like that.
Mr. Phung?
Yes.
So is this like chemo?
Chemo. So, not chemo, but nuke med,
Nuke med.
right?
Okay.
So nuclear medicine, they might have you swallow something, or they might inject something, right? And those might give off radiation, okay? And they'll give off specific types of radiation. But if it was something that gave off alpha particles, then it would be very, very dangerous. In fact, what was it? I think if you go online, you'll find stories of like back during the Cold War, you would have spies that would have like these radioactive umbrella tips that they could like stab someone, and they would inject a radioactive item like polonium that gives off alpha particles. And now that the alpha particles are inside the patient's body in the bloodstream, it would just kill them, right? So that was a method of assassination back then. Yes, Jay.
Would it also irradiate people around them?
Yes, although if it's alpha particles, it's not as bad.
Okay.
Yes,
So
Shahid.
we started with saying that high LET radiation are not dangerous because they give away the energy.
What's the key word here? What's the key word in the sentence?
Because high LET radiation has a poor ability to penetrate matter. It is not as dangerous when originating
Or
outside.
penetration.
When it's outside the body, so it can't go inside the body. Oh,
So
I see.
if it comes from outside the body and it's emitting this way, not dangerous. But if I swallow it and it's inside the body,
Of course, it
now
will attack your
it's
cells and all.
Exactly.
I see.
So so here's a diagram kind of like showing low versus high LET radiation. So over here on this end we have low LET radiation. This is a beta particle because it's an electron, and it doesn't cause a lot of damage. It doesn't have a lot of interactions. Okay. On the other hand, here lots of interactions along this path. Right. This would be high LET. Right. So few interactions. Right. Low energy interactions versus lots of interactions. High energy interactions. Low LET. High LET, less dangerous, more dangerous, right? Less damage, more damage. So once again, right, if low LET radiation interacts with DNA, the damage is usually sublethal. Low LET radiation usually will not kill the cell. Okay. First of all, it has a low likelihood of interactions. Low LET radiation does not interact a lot. If it does hit the DNA, we just have single strand breaks which are repairable. So it's not that bad.
So you're talking in favor of X-rays. That's what you're doing with us
No,
right now.
I'm making sure that we have a proper understanding of the dangers of radiation. Okay? Comparatively, X-rays, which are low LET radiation, are not as bad as alpha particles, which are high LET radiation. It's just you won't encounter alpha particles in everyday life, unlike X-rays. Okay? So, alpha particles, high LET, so many more interactions. Okay, and these high energy interactions can cause double strand breaks, right? It can break both strands of our DNA. Remember, DNA is double stranded. And if it does break both strands, now it becomes very difficult for the body to repair. So high LET radiation causes damage that is much more difficult to repair. So one more time, between low and high, which type of radiation causes more damage to the body?
Hi.
High LET, yes. That's right. That's why you don't listen to Charles. He tries to trick you sometimes. Okay. So, okay, so that is the concept of LET, linear energy transfer, right? How much energy is given off by the radiation in a certain distance as it travels. The next concept we need to discuss is RBE, relative biologic effectiveness. Let's take a look at this term and break it down. When we talk about something that being relative, what does that mean?
Compared to something.
Right, compared to comparatively. Right, this isn't uncle's cousin's relative. Right? I mean, I know your parents might compare you to your cousins, but in this case, we're specifically talking about person A versus person B, or X-ray radiation A versus radiation B. Right? We're comparing two types of radiation. Okay, biologic.
Something
Oh, you're asking
right?
us?
physical.
Right, dealing with the
Physiology.
body, the cells, right? And then effectiveness, right? How well it causes a certain effect, right? So we're looking at two types of radiation, and we're comparing how well, how efficiently, right? How effectively they can cause an effect on the body, on cells. So if two people receive the same dose of radiation, okay, and the LETs of the radiations are different, the biologic effects are going to be different. Right? So if I receive 100 sieverts of X-rays versus 100 sieverts of alpha, actually, sorry, let me go back. 100 grays worth of X-rays. Ooh, that's a lot. Okay, let's stick with 1 gray. So if I receive 1 gray of X-rays versus 1 gray of alpha particles, right? Same dose, it's both 1 gray. But we just said which one is more dangerous?
Alpha particle.
Alpha particles. Okay, let's assume the alpha particles are inside me, okay?
Okay, right, there you go.
Right, so-
See, I was listening.
So, we expect the biologic effects to be different. Okay? And so to describe how different these effects are, we have relative biologic effectiveness. So, what we do is we have this reference value. This is what we base everything off of. Our reference value is X-rays at 250 kBp. Okay, so let's imagine that I'm a patient and I receive 1 gray of X-rays that were at 250 kBp. And now my cell has experiences certain effects. Okay, my cells experience certain effects. We then go to a different patient. They receive the same dose, 1 gray of radiation. But maybe this time it's 1 gray of alpha particles, or 1 gray of beta particles, right? Or maybe 1 gray of 50 kBp X-rays, right? Just something different. So they receive a different kind of radiation. And then we look at the effects in that patient, right? And so we compare it and we're like, okay, how much more likely are we to see effects in our new patient compared to that original 250 kBp patient?
The reference value
So the reference value is always 250 kVp X-rays.
Mr. Phung?
Yes.
When
Shaheen.
you started, it sounded like you're going to put the same amount of X-ray in two patients and compare whether it affected them differently.
So
When you
it's not-
started it, did
so
you say like that?
Same dose, but different types of radiation. We're comparing, right, relative, we're comparing two kinds of radiation.
The radiation.
And I want to be able to say radiation B is 2 times more dangerous than radiation A. But how do I know it's 2 times more dangerous? I needed to have this comparison. I'm comparing this new one to my original 250 kVp X-rays. Yes.
So, sorry, this ties into the radiation weighting factor.
So this does tie into radiation weighting factor, yes.
Okay.
Okay. So if we look at this equation, RBE, dose in gray from 250 kVp X-rays versus dose in gray from radiation of interest. So let's say I want to say, okay, sterilization. How much dose in grays, in X-rays, would it take to cause temporary sterility in a patient? Yeah, about 2 grays.
Yeah.
So, I'm going to give a dose to a patient, and my question is, how much dose is needed to cause temporary sterility? So I give X-rays, and I find out, okay, it takes about 2 grays to cause temporary sterility. I now have a new kind of radiation. Let's call this radiation X. Okay, that's confusing.
Yeah, it
Let's
really
call this
is.
radiation alpha. Alpha radiation, okay, so it's an alpha particle. I have alpha particles. I want to know, okay, how many alpha particles does it take to cause the same effect? How many alpha particles until we get temporary sterility? And so I give a dose, and I find out, and that dose goes down here. Now, because alpha particles are more dangerous, do you think I need more of them or less of them to
Less
cause the
of
same?
them, sir. Less of them.
That's right, way less. I need a way less, and I can still cause sterility. So I have a dose up here, which is about 2 grays. I have a dose down here, which is way less than 2 grays. I divide, and that will give me my RBE. So if this is 2 grays of X-rays, and maybe I only need 0.2 grays of alpha particles, right? So 2 divided by 0.2. If you stick that in your calculator, what do you get?
2 divided by 0.2 is 20 divided by 2 is equal to 10.
You get 10. So your RBE would be 10. So you can now say that I need 10 times less dose in alpha particles, and I can still cause the same effect. Right? Alpha particles are like 10 times more dangerous because they can cause this effect with 10 times less dose.
Why can't they say it that way instead of doing it this way?
So you'll just say RBE 10, and then you would just understand 10 times more dangerous.
Yeah.
I don't even know what happened.
Mr. Phung.
All right, let's.
Mr.
Yeah,
Phung,
go
one
ahead.
question.
So let's
Mr.
try.
One
Stop.
question.
Let me finish. Let me do this first. All right. So let's try an example, and then after the example, let's clear up any confusion.
Okay.
So we've got a biologic reaction. Okay, it can be anything that is produced by 0.5 grays of test radiation. Okay, so our test radiation is the radiation that is our new radiation, the thing that we're looking at. It takes 0.8 grays of our 250 kVp X-rays, so our reference value, to produce the same reaction. Okay, so my reference X-rays, 0.8 grays. My new radiation that I'm testing, 0.5 grays to cause the same reaction. So, what is the RBE? Like you said, what goes on top?
250.
Our
0.8
0.8.
minus
Oh.
0.5.
What goes on the bottom? 0.5, right? And it is
So
1.6.
what are you minusing there, sir?
That's not
There's
a
no
minus.
minus, it's
That's
X-rays.
It's already there.
it's
X
just
dash rays, it's not a minus sign.
Oh, that's X-rays.
But did I skip it?
There's already a big mistake.
Oh,
Hey
okay.
now.
Okay, let's skip the first one. Sorry, I'll go back. Okay. But, right, we can see that our test radiation, this new radiation, is 1.6 times more dangerous than 250 kbp X-rays, right? Because we needed less of it to cause the same effect. So it's more dangerous, it's more potent. All right, let's go back to the first example.
Just times, that's.
Correct, that's right, this does not have units. The units end up canceling out when you divide. Right, sorry. So, okay, so this was the first one that I somehow skipped over. Okay, here we say we have a reaction caused by 2 grays of test radiation. It takes 10 grays of our reference, right, the 250 kbp, to cause the same reaction. What is the RBE of this test radiation? So reference, right, is 10 grays. The one that we're interested in, the one we're testing for,
It's, okay,
is only 2 grays.
so it's 5, okay.
So 10 over 2, 5. So this new radiation is 5 times more dangerous than our 250 kbp X-rays, right? We need 10 whole grays of 250 kbp X-rays to cause something to happen. But we only need 2 grays of this new radiation to cause the same effect. Right? This new radiation is 5 times more effective at doing this thing. It's 5 times more dangerous. Right? Yes, Johns.
Is that question always going to have 250 kbp on there, or can that change?
It is. It is always going to be your 250
Be louder
kbp.
next time.
Yes. Reference is always 250 kbp.
I couldn't hear you.
Be nice. Be nice. Okay, so yes, reference is always 250 kbp.
So if you have a figure, different figure, then you can always bring it to a 250 kbp equivalent. But we're not asked at that level.
Don't worry about that.
We'll just go direct.
Okay. Right, so kind of like what Jay mentioned earlier, this relative biologic effectiveness is very similar to our radiation weighting factor. And in fact, the radiation weighting factor is based off relative biologic effectiveness. However, there's a difference, right? Because both of them tell you like how much more dangerous one radiation is compared to another, right? Relatively effectiveness. But RBE also depends on tissue, while radiation weighting factor does not. Right? So radiation weighting factor, remember,
Combination of
is what we use to go from absorbed dose to equivalent dose. What is the purpose of radiation weighting factor? To tell you how dangerous your type of radiation is. And that is also the purpose of RBE, to tell you how much more dangerous your radiation is compared to the default 250.
But RPE has to do with the type of tissue.
RBE also is affected by the type of tissue.
So how does that go into the equation that you just gave? That was the one that
This equation here?
yeah.
So,
That changed the whole thing.
I mean, so the thing is that, right, this biologic reaction is going to depend on the kind of tissue, right? It's like, I'm trying to cause a reaction like, okay, cell death. And it's going to be a lot easier to cause cell death in intestinal tissue versus in brain tissue, right? So we would look at biologic reactions in intestinal tissue, and we would have an RBE to compare the radiation effects in that. We would then do experiments with brain tissue, and we would have an RBE comparing radiation in brain tissue.
But
Right?
also, it could be like a biological reaction in whatever kind of tissue is produced.
Correct. So,
But it changed the numbers.
yes, it would change. So yeah, numbers might change, right, depending on the kind of tissue you're looking at. So that's why RBE does depend on the tissue. But radiation weighting factor is based off these RBE tests, and radiation weighting factor is just a general way to describe how much more dangerous one kind of radiation is compared to the other. So if you remember, right, X-rays, radiation weighting factor of 1. And that makes sense now because we're using X-rays as our reference value. So the X-rays, of course, are going to be 1. Everything else is based off this 1 from our X-rays. right? So alpha particles are like 20, neutrons can be anywhere between 5 to 20, right? Beta particles, gamma rays, also 1. That is, yes.
This is kind of excess information, but X-rays came first, right? Before we really discovered alpha, beta, and neutron, like particles. Because then how would they
I
use?
think alpha looks old.
How would they use X-rays as a reference if it came after the 3?
So I'm not sure which particle was discovered first, although my guess as to if we're talking about properly identifying them, my guess would probably be X-rays, since the proton in the nucleus itself wasn't discovered until the 1900s.
Oh, okay, cool.
Right? Go back in your PRE book, it talks about Rutherford and the Gold-Foyle experiment.
Yeah.
Yeah. But as far as this goes, I mean, these weighting factors, this relative biologic effectiveness, these naturally came much after
1896 X-rays.
we had already 18 what?
At 96.
96 I said, sir. 1896.
What happened in 1896?
X-rays were discovered. 1986.
I'm sorry.
1896.
That was my fault.
Hey,
1786.
I'm sorry. I got us derailed. That's my bad.
Yeah.
I'll take responsibility for that.
Okay, yes, Jay.
1895.
I'm taking
Good.
responsibility for
All
that.
right.
I have a
That's my bad.
question.
Yes.
Let's
you
just
will.
recap.
Yeah.
Yes, recap.
Recap. Radiation weighting factor is a general way to describe how much one type of radiation is more dangerous than another.
Correct.
Let's just recap it.
Correct.
Thank you, Chara.
Okay. So RBE, very similar to that as well.
Yes, I did. RB, I got, describes how well different LETs can produce a particular
Okay.
reaction.
Sure. Let's take a 5-minute break.
Yeah.
I don't know what's
Five.
I just need to recap because I'm trying to get these
We'll take a
down.
5-minute break. Go use the restroom. Break.
No let.
We talked about
yes,
RBE.
let.
Okay.
Yes,
Yeah,
let
okay.
and RBE. Right. So today is going to be all about the 3-letter abbreviations.
I love
Let.
you.
Then your energy transfer.
And
RBE,
OER.
relative biologic effectiveness. And then finally, we're going to talk about OER, which is oxygen enhancement ratio.
Yep, that.
Right? All 3 of these are ways to
Oh.
describe how dangerous radiation is, right, comparatively. So OER, oxygen enhancement ratio. This one is very, very interesting because it's almost opposite of how you would imagine things to work. There is this thing called the oxygen effect. And I mean, cells need oxygen to function, right? A healthy cell gets lots of oxygen, it can do all of its tasks. A kind of unhealthy cell doesn't get all the oxygen it needs, so it's hypoxic, right? It's kind of slow, it's sluggish. So between the healthy cell and the unhealthy cell, if they were both to be exposed to radiation, which cell do you think is going to recover faster?
Healthy cells are there.
Right. You would think the healthy cell would recover faster. But here's the trick. Because tissues that are oxygenated, tissues with lots of oxygen, are actually
that's the
more
oxygen
sensitive
Yeah.
to radiation. So be careful, right? Because common sense tells you that healthy cells should recover faster. But in reality, the healthy cell is the one that takes more damage. Okay? Low oxygen cells receive less damage from radiation. Yes, Jay.
Does that have anything to do with oxygen's effect on like the DNA in the cell, or is that more so just a generalized thing?
Hang on to that question.
Damn.
So, oxygen enhancement ratio describes the ratio of sensitive between a cell with oxygen versus without oxygen. Right, so now we're looking at a cell, we're looking at radiation, and we're talking about, okay, this radiation, how different is the damage of the radiation without air versus with air? Okay, so I've got a cell, one cell has air, one cell does not have a lot of air. Same radiation hits both cells will experience an effect, but the one with the oxygen will experience the bigger effect, The one without oxygen will experience the smaller effect.
Do we have to know that the OER?
Mhm.
Radiation dose and oxygen?
Right, so it is how much dose to cause an effect while there's low oxygen versus how much dose to cause an effect while there's plenty of oxygen. So this is very similar to RBE, right? Once again, we have a reaction, right? This reaction can be anything, okay? Maybe cell death, but we have a reaction and 2 grays of X-ray can cause this reaction when the cell has air.
I didn't mean to say hey.
However, it takes 6 grays of X-rays, the exact same X-rays, to cause this effect when the cell has low amounts of air. Right, so 2 grays when it has lots of air, 6 grays when there's low amounts of air. As you can see, as the amount of air the cell has decreases, it takes more radiation to cause the effect. So what is the OER in this case? So, how much dose was applied when there was no air?
6 grays, sir.
6 grays. How much dose was applied when there is air?
2.
2, right? So 6 over 2, that gives us 3. So the cell is 3 times more sensitive with air compared to without air. Okay, so the more air the cell has, the more sensitive it is to this radiation. Yes, Jay?
And this is without taking the type of tissue into account?
So this is without taking the type of tissue into account, right? We're looking at a specific biological reaction.
Okay.
So like in this, so this thing in this cell, how much effect will there be oxygen versus no oxygen?
So then 3 is not a generalized summation?
Yeah.
Okay, cool.
Right. But I mean, we can use it, generally speaking, to look at patterns, right? That's what OER is very useful for, looking at patterns. Because what we notice is when we have radiation that is low LET, right? When we have low LET radiation, we find that the OER is relatively high. We have OERs of 2 or 3. That means the cell is 2 or 3 times more sensitive to radiation, to low LET radiation, when they have oxygen. So there's this considerably large difference here. On the other hand, high LET radiation, we find the OER is about 1. That means there's no difference between air or no air. The damage is the same. Right? So low LET, oxygen has a significant effect on the cell's sensitivity. High LET, oxygen does not play a role. Right? So this is how we can use OER. We can use OER to describe low LET versus high LET once again. Now, of course, the question then becomes, why on earth does low LET radiation get affected by oxygen, while high LET radiation has apparently no effect from oxygen? Why does oxygen play a role in low LET, but not in high LET? Okay, Jay.
I'm assuming that oxygen, well, due to the presence of oxygen, it acts as a sort of like block. Like, similarly, like alpha particles can't come through paper. It's just another substance for it to travel through.
Okay. All right.
Or interact against.
All right. Good hypothesis. Cody.
Does it have to do with like the action that occurs, that indirect to direct?
Okay. So indirect versus direct action. So low LET would be what kind of action?
Indirect.
Indirect. And high LET?
Direct.
Direct. Okay. Yes. So let's think about how low LET versus high LET interacts with the cell. And to make this simple, let's start with high LET. High LET radiation manages to make its way into the cell. And once it gets to the cell, what is the most dangerous thing for the cell that this can interact with? The nucleus, and specifically what inside the nucleus? DNA.
Pow, pow.
That's right. This high LET radiation hits the DNA. And what kind of damage does it cause to the DNA?
It dies.
It dies.
Cell death.
All right. Remember earlier
Double
we
strand
said that
break.
it can like break both chains.
Oh yeah, bro.
Double
Break the
strand.
chains, the shackles.
Hey,
That's right, breaking
happy
those
February,
bonds.
y'all.
Right, so
Breaking them
DNA,
chains.
2 strands. High LET chops off both strands.
The math laughed a little too hard.
Right? And it's going to be hard for the cell to fix it because now the cell's like, does it go this way? Or does it go this way? Or maybe it goes this way? And the cell's lost now, right? The cell can't fix this. So, in high LET radiation, the radiation comes in, it does a whole bunch of damage that can't be repaired. And so oxygen really doesn't play a role here, right? Oxygen plays no role in this damaging aspect. It just comes in, blows things up, and leaves, or gets absorbed and disappears. Right? Oxygen plays no role, so the amount of oxygen doesn't matter. It destroys the cell no matter what. On the other hand, when we look at low LET radiation, we said that it's these indirect actions that cause damage to the DNA, right? The X-rays interacting with water, the water creating free radicals, the free radicals chemically attacking the DNA to cause damage. So because it's taking this indirect process, now oxygen has a chance to play a role in this process. And we suspect what happens is that when damage is caused by these free radicals, right, so maybe like single chain break, normally a single chain break, the enzymes can put it right back together. The enzymes can fix it. But now, while this break exists, oxygen can come in and bind, right? It can have a chemical reaction to this open DNA. And if it does that, now this strand can no longer go back together. It's kind of like wedged apart, right? There's this oxygen that's in the way, keeping it from properly closing anymore. And so that can increase the damage. Of course, the more oxygen you have, the more likely it is that this can happen, right? This thing called the oxygen fixing, right? Oxygen attaching itself to the DNA and keeping it from healing. So the more oxygen you have, then the more of an effect we see. The less oxygen we have, well, there's no oxygen to get in the way, so we can repair the DNA normally. Does that make sense?
Oh.
Okay, we'll try again later. Yes.
Normally oxygen.
Hold on. Wait. Yes.
Okay, so if this is off topic, not off topic, but off this topic, because I don't understand this, but so if the radiation, like for X-rays as a whole, is low, what makes like fluoro and stuff so dangerous? Is it just the amount of X-rays?
It is.
Okay, but
It's just pure numbers. You just have so many X-rays over such a long period of time that you have more damage, or likelihood of more damage.
likelihood. So if we do the same thing, it's just it could randomly interact.
Right. So, last semester, did you talk about stochastic versus tissue effects? Right. So stochastic being your random effects like cancer, and then tissue effects being your kind of like guaranteed effects at certain dose levels.
Oh
Right.
yeah, we did. I remember that.
Yeah. Right. Deterministic, although we don't really like to use that term anymore because it's not purely deterministic.
Does it can be random?
It's kind of, it's not entirely random either, but it's,
Some, it can be partially random.
yeah, partially, yes,
Yeah,
we'll call it partially.
that's a good word to use, partially
Yes.
random, yeah.
Yeah, so deterministic isn't a great descriptor of what's going on.
That's why I like to use
So,
it.
yeah, we don't call it non-stochastic or non-random or deterministic, we just call them tissue effects now. But yeah, stochastic, your random effects, that's your cancers, right? Tissue effects, that's gonna be your erythema, right? Reddening of the skin. So, both of them are gonna be more likely to happen when just the dose goes up. And as we said, dose is primarily based on just pure quantity of X-rays.
So still less dangerous than alpha particles that are inside.
You know, alpha particles are, so that's where our comparison can work then, right? So it's like, okay, you need 20 times more X-rays compared to alpha particles. Right?
Okay.
One alpha particle has the effect of like 20 X-ray photons. So if it's just like 1-to-1, X-rays are much less dangerous. But if you have a whole ton of X-rays, then yeah, the damage builds up.
They make it seem like it's so much different.
So this is just,
Like alpha particles are so dangerous with X-rays.
Mhm.
No, it's fine, it's safe. But I mean, in
Right.
reality,
so yes, just keep in mind that number one, how likely you are to run into them. Alpha particles much less common, right? Especially for us, because we work in radiology. X-rays are going to be the most common radiation we run into. And then secondly, right, just sheer number.
We going down.
What is that? Going down?
Yes, we're trying to stay alive.
Alright.
We're trying to stay up.
Oh,
Okay,
I forgot
so-
what rotation I was
So
in. There was a
basically-
baby. It was like a newborn, and I forgot who else, but they said that they were taking X-rays of that baby like every day, basically.
Mhm.
Isn't that like dangerous?
Yes, so the dosimetrist or the physicist, medical physicist, should be monitoring that. Right? And so,
Should they?
and so if the exposures get to a certain level, then it just becomes a matter of medical necessity. Right?
is it life or death?
Right, so basically in medical imaging, even your routine two-view chest X-rays, it's always a matter of trade-offs, right? So is the information we gain from this exam worth the risks? Like trade-offs, risk versus reward.
I'm guessing the
So-
information, that's always be worth it to them.
Right, so in the case of the baby, right, if it's a line placement, right, they're gonna need an X-ray to make sure that the line's in the correct place, right? If they're looking to monitor something that can be only determined radiographically, I can't give you an example since I don't know it in such detail.
Okay, but like, what if they have like their clavicle's broken? It's not gonna heal from one day to the next, right?
Right. Yeah, at that point, if you see them ordering an X-ray every single day, being like, monitoring clavicle healing, then you might be like, do you need this like every 24 hours, every 12 hours?
Really? I saw that happen.
Right? So,
Yeah.
I
I saw
mean-
them order an X-ray on a set of twins. Is that monozygotic? Is that how you say it?
monozygotic? Uh-huh.
Yeah. They passed away, but they had an X-ray twice a day
Mhm.
before they became deceased. And I was like, why the heck are they taking so many X-rays of these babies?
That's
What's
it.
wrong with them?
So many things.
Well,
Yeah.
That's
Yeah,
unfortunately
but question
probably
now.
why. Right? Because at that point, sorry, I'll get you in. Because at that point, then it becomes like long-term versus short-term, right?
Mhm.
Like, sure, you're doing a lot of X-rays. In the long term, you could cause some future problems.
Mhm.
But right now, with so many things going on with the baby, we want to try and get the baby through this period.
Or do we know that the success rate is not high? So maybe we can save another baby if we take a lot of X-rays of this baby and figure out what the cause was here and how to fix it, and then maybe I'm just gonna get to the
I
benefit of the
mean,
doubt.
that's always possible, right?
Yeah.
Or, okay, and this is the most cynical take on it.
Yeah.
It could just be CYA, right? Baby is probably gonna die, but we're gonna show that we did everything that we could.
Our own,
Right?
Posterior.
We're gonna show we did everything we could to save the baby.
yeah, it was two, both of them passed.
So,
Oh. Sad.
but of course, if you want to understand the medical necessity of those X-rays, the person you should talk to is the ordering physician.
I have talked to several ordering physicians and.
Okay, but before we get any further to that, right? That's gonna be a conversation for after class.
Oh,
Yeah,
yeah.
Shaheen.
So normally oxygen is positive for human tissue.
Yes.
But in this case, it's working negatively.
It's working against us, yes. So that's why I said this is kind of a really weird effect. it goes against what your common sense would tell you.
And that's the oxygen effect, correct?
Oxygen effect, yes. All right, so
What is our next test?
depends on how quickly we get through this chapter.
I don't know. that would be
Stall
kinda
him,
rough.
stall
That's
him.
one chapter.
Stall them.
How many questions?
I don't know yet. That's a question for another day. So,
I feel like that's a better question.
sorry, I didn't mean to be rude, but I do not know how many questions will be on this.
Reagan had a question for you.
Yes, Reagan.
How many more slides do we have?
So we have covered up through slide 18.
Oh, we're on a roll.
Have you sent this out to us yet?
Yes.
Yes, I did. All right.
70 slides, by the way.
It's not that bad. A lot of the slides are just like single
Pictures.
pieces of information
Yeah.
near the end.
52 slides left.
And there are gonna be a lot of pictures here. And I'll be honest, this next part, I'll tell you the key takeaways. Not everything in this next part is gonna be extremely important. But,
Not, have you highlighted with
So-
red, sir?
right, you highlight yourself when I point these out to you. Okay, so, we were talking about molecules, right, specifically DNA. And yes, right, damage to things like DNA, right, damage to our molecules is what causes damage to the organism as a whole, right? If something happens to me because of radiation, it's because the radiation damaged my molecules. Now, looking at the cells that these molecules belong to, right? Different cells have different functions. So depending on what the radiation interacts with, the radiation can have different effects, right? If it hits a molecule in one cell, it could have a different effect than hitting a molecule in a different cell. Just depends on the purpose of that cell. Okay. Radiation can disrupt the chemicals inside the cell, and so now the cell can't properly carry out its job. For example, if we have body cells, and the body cells are no longer able to do their job, then we will have problems throughout the body, right? If it damages the blood cells and the blood cells can't carry oxygen anymore, or they can't fight disease, then we will see those effects in the body. On the other hand, if the radiation affects germ cells, right, our sexual cells, then we won't see effects in our own bodies, but we'll see effects in the next generation, the future generations. Yes, Jay?
Those are called genetic effects.
Genetic effects, yes. So somatic versus genetic effects.
We gotta learn those things in here.
What do you mean? Genetic effects? Yes, yes we will. Yes, both effects, yes. Somatic effects will primarily be chapter 8, and genetic effects I think will be chapter 9.
What about that threshold and non-threshold?
That is gonna be chapter 8 or 9, I believe.
You get a lot of points for
Okay, so once more, kind of as a review, 2 ways for radiation to damage a cell: direct action, indirect action, right? It's DNA versus it's something else like water. So direct action, right? It can hit these important molecules. Now, RNA, proteins, enzymes, these aren't as important because you have lots of RNA in the cell, you have lots of proteins in the cell, you have lots of enzymes in the cell. But you only have one copy of the DNA. So DNA is the most important molecule out of these 4.
Massive.
That's right. So, enzymes, right? If enzymes are affected by radiation, they can change shape, they can't do their function anymore, but not a big deal. You have lots of these enzymes, right? So, DNA is the most important thing in terms of direct action.
In a sense, sir.
In the cell, yes.
And if there's only one DNA, but the RNA is how many, sir?
Lots. You have lots of RNA. Okay, now indirect action. This is the fun part. So, indirect action, primarily caused by radiolysis of water, right? Radio being a radiation, lysis being to cut. So radiation is us breaking apart water. So Carla, what is the chemical formula for water? H2O, yes. H2O. Okay. Before we talk about radiolysis, we have one final fun chemical thing to talk about, which is free radicals. Free radicals are not ions. Okay, so that's the first important thing to keep in mind. Free radicals are not ions. They do not have a positive charge. They do not have a negative charge. They are electrically neutral. However, what they are missing is an electron. They are missing an electron in the outermost shell, in that valence shell. So, you notice in each of these boxes you have a pair of electrons, right? A pair of electrons, but what happened over here?
Gone.
It's missing one. So, this is an example of chlorine. Okay, chlorine here has, what is this? 17? Yeah, it's got 17 electrons. Okay, it's also got 17 protons, so it has no charge. However, it really wants to finish off that last box. It really wants to get that final electron in that final box. That's what makes this a free radical. Even though it has no charge, it really wants an extra electron. It wants to be negative. It wants that extra electron. And it wants that electron so badly, it is willing to go to other atoms and beat them up and steal their electrons. It is going to go and pull a GTA and mug those other atoms and steal their electrons. My sister plays it.
Okay.
Your sister?
Yeah, she's got like the garage full of pink
Your
cars.
sister is like a thug. She plays GTA.
She plays GTA, she plays Cyberpunk, she plays
Oh
all
my god.
Oh,
Yes,
Mrs. Fung,
Jay.
if you get into a fight, bring your sister. 'Cause she gonna win.
Free radicals are anything that has just one valence electron.
So it is missing a valence electron.
It's missing
or-
a valence electron.
So it's either missing a valence electron or it has an extra valence electron.
So 7 and 1.
7 and 1. That's right.
But the outer circle always must have 8. So it's not missing.
So it does
Up
not
to.
always have 8, but it wants to have 8. And that's why it's wants that extra electron so badly. It's got 7
so
on
to
the
make
outside.
it stable, right?
That's right, it wants to be stable. It really wants that 8th electron. And so it's willing to steal it from other places. Okay, and we'll go ahead and stop there for today.
So radical steel.
That's right, they're radicals, right? They're gonna radically go around and radically steal things from other non-radicals.
Okay, I like that.
But do they actually ever get the electron, or are they just roaming around?
They do. And it's because they do get the electron that it causes trouble for the body. Because if this free radical happens to be next to a juicy piece of DNA, it's just going to mug that DNA and steal an electron from the DNA. And now that the DNA is missing an electron, it will cause the chemical bonds in the DNA to break. And because now you've broken the chemical bonds in the DNA, now you have a problem. Yes, Jay.
So is that a single strand, double strand? Or does it have a specific sort of break if it comes into contact with them?
So it causes any kind of breaks, single strand, but if it causes one break here and then it causes another break here in close proximity, both in location and time, then you could get a double strand break.
So did you say ions are like positive and negative radicals have a dot in front of them?
Correct. Ions are positive and negative. Ions
But
have a dot.
we've never seen radicals with a dot.
There you go. You see it on right now.
So this is not in the place of where the positive and negative is.
This is in place of positive and negative.
I see.
So here, I'll show you one of these fun slides up here.
Yeah, that's
Right. You're used to seeing this, which is H plus, that's an ion, but you also have H dot, which is a free radical, right? So
First time
H
I
plus
see this,
and then OH dot.
No high school chemistry taught us that though.
All right, well, you are beyond high school chemistry now.
Looks like it's
All right, but yes, we are done.
Someone,
Take
pressed
a-
on the door, on the ring
Okay,
bell.
let me go and take a look. All right, enjoy your 15-minute break. Please remember, these are due on
15-minute break.
Thursday. 15, 1 5.
Oh, I was gonna say.
I'm not that generous.
Mm.
He said, not that yet.
I see how you've escaped the Laura questioning. Uh-huh. Uh-huh.
So it's going to be back for the class?
Just a
No,
reminder,
we're done.
we have the email for the survey.
Whoever's presenting, get ready for some questions.
That
Me?
is, Clayton sent.
Yeah, I'm first.
He said he's coming back.
Oh, I know. He's
But Ms.
he's.
Smith said that no questions.
Listen,
I welcome questions. I welcome
today,
questions.
the questionnaire that Ms. Clayton sent is due today. for
Ms.
the end of the
Josephine.
day, for
What
the yearbook.
questionnaire?
It's just
Joseph,
gonna be due.
Why is she always so quick with that stuff? It's always like
It's
one
just
day.
gonna be due.
Because she's had that sitting on her
miss your
inbox for the
doctor.
last couple months and
Got a notification
I
this
miss
morning.
Samantha's doctor.
Yes, I'm